everyone. Thank you for being here today. So my presentation today is basically going to be on the sun, and I hope you listen carefully because at the end of it, there's going to be a short quiz. It's not going to be too difficult, and then but I have a few prizes that I'm going to give up. Just pull it on right now. We'll be giving these out to each correct answer from the quiz. I'll be talking a little bit more about these as well. Okay, so before we start, I'll just request that if you have any phones that are not on silent, you just put them on silent so that we don't have any disturbance throughout the presentation. Alright, then let's get started. So this first section, I just want to talk about how important the sun is. Obviously, we all know how important the sun is in the solar system, but this is just me, in a sense, quantifying how important the sun really is. So if we were to start off by mass, the sun takes up 99.8% of the entire solar system by mass. So if you were to take Mercury, Venus, Earth, Mars, Jupiter, Saturn, all these 8 planets, you were to take all the moons, you were to take all the asteroids in the solar system, you were to take all the comets, you were to take all the dust in the solar system, and you were to combine it into one body, that would only weigh 0.2% of the solar system, and the sun would take up 99.8% of the solar system. So by mass, the sun practically dictates the solar system. In terms of its influence, both hard influence and soft influence, first off, energy-wise, the sun provides 99.97% of the energy that we use on Earth, either directly or indirectly. So if you were to look at solar energy, wind energy, even non-renewable energy like fossil fuels, they are indirectly fueled by the sun. So 99% of our energy use on Earth is provided by the sun, and the other 0.3% is provided by other sources like radioactive decay and tidal energy from the moon. And the other important thing is that the Earth is in the sun's habitable zone. So this is basically a zone in the sun's influence where it's not too hot and it's not too cold, which means that we are able to survive without being burnt or frozen. The other thing the sun does is it protects us. I'll be talking a bit more about this, but the premise is that the sun has solar wind. It blasts solar wind out into space, and that solar wind forms a bubble around the solar system. We call that bubble the heliosphere. And this bubble is basically a shield from any interstellar rays and cosmic radiation that might threaten life on Earth. So we have protection in that sense as well. And obviously, historically, the sun has been pretty important to us. Think zodiac signs, think agriculture, think timekeeping, think sundials. We've used sundials to keep track of time on a daily basis. We've used zodiac signs and constellations to keep track of time on a yearly basis, and we've also used that to guide agricultural practices. So the sun obviously is very important to us in that matter. Another thing is auroras. I'll talk more about it, but auroras effectively happen close to the North Pole and the South Pole. Close to the North Pole, we have civilizations like Norway, Sweden, and Finland, and in their culture, auroras are deeply ingrained because of the sun. A few more things. Obviously, water. The sun drives ocean currents across the globe because it unevenly heats the air and the ocean. So as a result, it regulates Earth's climate, and the sun also powers the water cycle. Most of you have seen an image or a diagram of the hydrological cycle. You'll see the sun probably hanging out in a corner over there. The sun is pretty important to the water cycle as well. So it replenishes freshwater sources across the globe, such as rivers and lakes. And then, when the planets were also being formed, we had solar wind play a role there, because what solar wind did was it applied a pushing force to elements in the solar system. So what you had was gases like hydrogen and helium being pushed further out to planets like Jupiter and Saturn, and rockier elements and more heavy elements like oxygen and carbon stayed further inward. So in that sense, the sun has shaped the planets as they are. So the reason Earth is a rocky planet and we have a surface to stand on is because the sun pushed away those lighter elements and left elements like oxygen closer to the sun. Another point that I'll dedicate a whole section to is what we call the "we are made of stars" stuff thing. So what's happened is, in the core of every star, we're fusing hydrogen into helium, and as a star approaches its end of life, it begins to fuse helium into other elements as well, such that when the star eventually dies, it distributes all of these elements across the cosmos, and then those elements will eventually be recycled to create new planets and you and I. But I will talk about that. It's a really interesting section. Obviously, before we move on to the next section, the word solar system comes from the sun, because the Latin word sol means sun. Okay, so now we're going to be talking about a mechanism in the sun that is core to this entire presentation. So I'm going to be detailing how the sun's magnetic field is formed, how it's distorted, and how the sun's magnetic field causes everything that we see in the solar system, directly and indirectly. For reference, this video is of the Earth's magnetic field, and what you see is solar wind. This isn't the animation of the sun's solar field. Okay, before we move into that, I wanted us to just quickly get an overview of the sun's layers, since we will be referencing that quite a bit. So we've got 6 layers. We've got the core, which is the hottest layer in the sun. This is where the nuclear fusion actually takes place. You'll have hydrogen being fused into helium. Then above that, we've got the radiated zone. I'm sure most of you have heard the 3 methods of heat transfer. You have radiation, convection, and conduction. So the sun takes 2 of them. The sun has a radiated zone, where radiation takes place, and then a convective zone right above that, where convection takes place. Then above that, we have the photosphere. It's called the photosphere because that's the layer of the sun we see. Above that, we have the chromosphere, which is the layer where all solar activity takes place. All solar weather, you'll see stems from the chromosphere. And above that, we have the sun's atmosphere, which is the corona. So that's just a brief overview of the sun's layers. So now, talking about the magnetic field, we're going to talk about a phenomenon called differential rotation. It sounds complex, it's not really. Differential rotation is basically the principle that the sun is not solid like the planets are. So obviously the planets rotate solid. If I'm sitting in Norway or if I'm sitting in Equatorial Guinea, a day is still 24 hours for me. But if you're on the sun, as you can see in this graph, it's pixelated, but this area is 24 days and this area, the red area, is 34 days. So what this diagram is showing us is that the equatorial areas of the sun rotate once every 25, 24 days, and the poles rotate once every 34 days. So differential rotation is saying that parts of the sun rotate at different speeds. And what this leads to is a tangling of the magnetic field lines. So obviously, if I'm pulling one side of a carpet faster than another side of the carpet does eventually become wrinkled. And that's sort of what's happening here as well, except it's happening with the magnetic field. Another phenomenon we can see within the same visualization is on the other side. You can see the convective zone. This is the convective zone. So what you're having here is hot plasma. Plasma is being heated here towards the core, and then as it's hot, it's rising up towards the surface, and it's transferring its heat towards the outer layers. And as it transfers this heat, it cools, it sinks back, and it's reheated, and it comes back to the surface. And this cycle is sort of a churning motion, and this also drags magnetic field lines along with it. So now if we were to combine these 2 effects, the convection currents as well as the differential rotation mechanism together, we get what we call the dynamo effect, which basically is the sun's magnetic field constantly changing, constantly breaking, constantly being rebuilt. And this causes a cycle of the sun's magnetic field rising, peaking, and then waning. So if we take a look at this bottom graph here, not the top one yet, in the bottom graph you can see quite a few peaks and quite a few troughs. So at the peaks, this is when solar activity is at a max, and at the troughs, this is when solar activity is at a minimum. And at this entire cycle, from minimum to minimum again, takes 11 years. And we call that the solar cycle. And an interesting thing to note here, and I'll show you a visualization in a sec. With every solar cycle, the magnetic field flips once. So if in 2025, the sun's north pole, magnetic north pole faces upwards in a sense, then in 2036, which is 11 years from now, magnetic north will be the other way around. Now, if we were to double this cycle, if we were to take 11 years and make it 22 years, that cycle is called the Hale cycle. And what's interesting about the Hale cycle is, after one Hale cycle, the sun will return to its original state. So if another 11 years pass by, 2047, then magnetic north will point up again. So what that looks like on the graph is basically 2 peaks. So you'll have one peak flip it, and the other peak return it to normal. This is a visualization of the timing. You can see the year here. It started off in 2019, and you can see the green pole is pointing up. And as we're progressing, from 2019, if we want to see the magnetic fields tangle but not solve itself, we're going to have to divide 11 years by 2. So that's 5.5 years. So from 2019, 5.5 years is mid-2024. So you can watch as the time is progressing. When in April of 2021, you can see the magnetic field is becoming more and more tangled. You can see more of these green lines headed south and more of these purple lines headed north. Obviously, now we're halfway through that, so now we're headed into 2022. And you can see it becomes ever more tangled, keeps becoming tangled. Now we're in May of 2022. It's jittering a bit, but yeah, as you can see, it keeps going. September 2022, it's becoming even more tangled. You've got green magnetic field lines touch the southern side of the sun, and purple lines go closer to the northern side because they're ready to flip. And as we're approaching 2024, you can see this, it's complete chaos. So if I was to go to a before and after, you can see this is what it looked like in 2020, and this is what it looks like mid-2024. So you can see completely normal and completely tangled. Now I want us to visualize that 11-year cycle. This is much older footage. You can see we're starting off in 1997. So thing to note is we started off with the green pole at the top, and now as time progresses, it's flipped. And by the time 2008 rolls around, which is 11 years later, the green pole's at the bottom. And here's another before and after. You can see over there 1997, green pole's on top, and in 2008, green pole's at the bottom. Alright, so that's basically how the magnetic field of the sun works. Now I want us to explore how some of these phenomena we see across the solar system occur from the magnetic field. So sort of establishing a link between these phenomena and this mechanism. First off, we have solar flares. So solar flares are basically intense bursts of radiation where you have a lot of energy released, and the energy is the equivalent of millions of hydrogen bombs at once. So if I was to put this little visualization into perspective, that little ellipse you see there, Earth would comfortably fit within that. That's how big the solar flare is. They're formed when oppositely directed field lines break and reconnect. So what's happening is you had this be a huge magnetic field line, and the top here will break, and this side will connect to this side, and this side will connect to this side. So now you have this independent sort of area of charged particles that now headed outwards towards the rest of the solar system. And yeah, this results in radiation being emitted across the electromagnetic spectrum. We've got 3 types of solar flares, and you can see this is a real life solar flare over here. We've got X-class flares. These are the most powerful flares to exist, and these, if we were to be impacted by an X-class flare, you'd have planet-wide blackouts. So you wouldn't have electricity, you wouldn't be able to listen to the radio, banking systems will be down. The entire digital world will collapse if we had an X-class flare with us. After that, we have an M-class flare. These are more moderate flares. We see them a lot more often, and these are capable of causing brief radio blackouts in polar regions because these are not as powerful, so they can't impact the whole planet. So they'll impact areas like Norway, like I mentioned, and Antarctica. Less powerful than that, we have C-class flares. These are super weak flares. You'll barely notice them. Yeah. This is an animation of a solar flare in 3 different wavelengths of light, just so that you can see how it looks. It happens really quick, but if you were to notice, you'd see it break, reconnect, and charged material just be released super quickly. Like this. Yeah. Alright, moving on to the next phenomenon, we've got sunspots. So as you can see, it's pretty self-explanatory. These are spots on the sun. They look darker than the surrounding solar surface, and that's because they're cooler in temperature. So these usually exist in pairs because these are directly linked to magnetic field lines, and they occur where convection is inhibited. So what that means is, if I'm inhibiting convection, the hot plasma that I was talking about when I was talking about convection currents, that won't rise, and as a result, that heat won't be transferred to outer layers. So in that area, you won't have that heat being transferred, which means that area will start cooling down and be cooler than its surrounding area. And that's how you have this darker region. And this, again, this is just an animation. This isn't proper footage. This is an animation versus proper footage. So this is the magnetic field line. This is what you see if you were to point a telescope at the sun, a proper telescope. And this is its sunspot equivalent. So I mentioned that they exist in pairs, and that's because you can see from one side you have the magnetic field line coming out, and from the other side it's entering the sun again. And that's how it looks like as a sunspot. This is alright, moving on to the more beautiful phenomenon. I'm pretty sure we're all familiar with this. This is the auroras. They're more commonly known as the northern lights and the southern lights. These are vivid polar light displays, and these are caused by CMEs. This is a coronal mass ejection. I will be talking about that in the next few slides. And what you need to take away from auroras, obviously we see different colors of auroras around the planet. We have green, we can see red, and we can see blue and purple. And these are basically affected by the element as well as the altitude. So if you were to have oxygen at lower altitudes, say 100 to 300 kilometers above the Earth's surface, then your aurora will be green in color. As you can see, most footage you see of auroras are green in color. You will also see red auroras, as I'll show you in a minute. These are caused by oxygen at a much higher altitude, which is 300 to 400 kilometers. The ISS, for reference, orbits the Earth at 400 kilometers above the surface. And obviously, we have blue and purple, but that's caused by a different element. That's nitrogen at various altitudes. So obviously, you can see a green aurora here. But if I were to show you, okay, I'll show you on the next slide. This is a visualization of what causes auroras. So you can see lots of charged particles are coming from solar wind and CMEs, which I'll talk about. And you can see they're being sort of funneled towards the poles. So as they're being funneled towards the poles, you can see they interact with oxygen and nitrogen in the upper atmosphere, and that causes the red and green and blue and purple lights that we see very beautifully. These are two images. They're not my images, but they are images of auroras in Cape Town. So this happened last year. This is a photo of an aurora in May, and this is a photo of an aurora in October. Obviously, as I mentioned, this is caused by oxygen, and this is caused by nitrogen. Obviously, because CMEs and solar wind isn't restricted to only the Earth, all the planets in the solar system experience it. As a result, other planets that have magnetic fields, like Jupiter and Saturn, also experience auroras. And this is real-life footage of what auroras on Jupiter look like. Okay, finally, we are going to talk about coronal mass ejections. So these are large-scale expulsions of plasma from the solar corona. And what that basically means is a coronal mass ejection is the sun ejecting material from itself into space. So it's basically throwing a part of itself into space at a very high speed at the planets. This is an actual photo of a coronal mass ejection. You'll notice we blocked out the center, and that's because the center of the sun is too bright, and if we were to look at the center, we would not be able to see the corona. So telescopes will block the center, and then you'll be able to see the coronal mass ejection. A difference between solar flares and coronal mass ejections is that solar flares will emit radiation and charged particles, but CMEs will emit billions of tons of solar material as a torch. And CMEs will compress the Earth's magnetosphere. I've got a visualization coming up to show you that, and that will cause geomagnetic storms. They can also have the same effect as solar flares, which is damage to radio systems, power grids, and the digital world. This is a real-life animation. Well, this is real-life footage of the coronal mass ejection. So you can see one's been released towards the right and the left, one's been released to the right, and now you'll see the camera capture one being released at the camera. Just about now. So this is what it looks like to take a camera and record a coronal mass ejection, which is billions of tons of solar material, all of these dots, solar material just being flung at you at a very, very high speed. You'll notice that it's got three different sort of colors here. You've got a blue layer, orange layer, and then you've got a green sign in the middle. That's because when we were recording this footage, we had to block out the sun. So we used other footage of the sun at the same time, pasted that in, and same story for the green footage. This is a visualization of the Carrington event. So the Carrington event is the most powerful coronal mass ejection we've ever witnessed in recorded history. So you can see all the solar material, and you can see the Earth over here, and you can see as it approaches the Earth is just deflecting all of it. So now if the Earth were unable to deflect all of it, what would happen is this would hit us, this will slash through our bodies, and it would cause a lot of harm after that. Obviously you can see Earth's meters here. So the Carrington event is reported to have happened in 1859, and if such an event was to happen today, we would be in an irrecoverable blackout. So we would have no power for months on end because we would be unable to repair our power grids failing at such a high volume. Okay, moving on to solar wind. So solar wind, as you saw in the title slide of the presentation, this is a stream of charged particles released from the corona. So this is the sun's atmosphere, and it's releasing all of these charged particles. So a few characteristics of solar wind is that it can strip the atmospheres of the planet. We like to say it is ionizing in nature, and it travels at 400 kilometers a second. So that's an important figure to remember. Solar wind travels at 400 kilometers a second, roughly. It's usually a range between 300 and 800, depending on how far it is from the sun, but a good figure to remember as well. Again, this is similar to solar flares. This is composed of electrons, protons, alpha particles. Alpha particles are basically a mixture of protons and neutrons. The main difference between solar wind and solar flares is that solar flares will happen once in a while. You see that sort of magnetic field line breaking and then reconnecting. But solar wind is just a characteristic of the sun. It always happens. It's a constant flow of wind. And solar wind, again, because it's charged, it can also cause geomagnetic storms on the Earth. So we've got three phenomena that can cause geomagnetic storms on the Earth. You've got solar flares, you've got solar wind, and you have coronal mass ejections. Okay, now moving to another thing caused by solar wind. As I was mentioning in the first section of the presentation, I was talking about the heliosphere being our shield in the solar system. So this is a vast bubble, as you can see. It's quite literally a bubble of space that is protected because solar wind is pushing outwards. We've got two boundaries on the heliosphere. As you'll see, solar wind zooming out. And we've got two boundaries here. We've got this inner boundary, and this inner boundary is called the termination shock. And then we've got this outer boundary, which is sort of bending in the direction of solar interstellar wind, because you can see all this wind coming and hitting the heliosphere, and the heliosphere protecting us from it. So what we call this boundary, we call it the heliopause. And what that means is, this is the actual boundary where solar wind is completely neutralized against interstellar radiation, and it's sort of no man's land, if you will. Okay, so now that we've talked about all these phenomena we see across the solar system, I just wanted us to revisit the sun's magnetic field and the solar cycle just a bit more, so that we can understand how the solar cycle works and its consequences. So the solar cycle, you remember when I showed you that graph, you could see a few peaks and a few troughs. So the troughs are solar minimum, and the peaks are solar maximum. Solar maximum is basically, as the name suggests, a period of maximized solar activity, and solar minimum is a period of minimized solar activity. So a few differences between the two. These are always 5.5 years apart. A few differences between the two. In solar minimum, the magnetic field of the sun is not tangled. If you remember that visualization, you'll have the green pole be perfectly upward and the purple pole pointing perfectly downward. But in solar maximum, it's chaotic. Solar phenomena and solar weather are less frequent during solar minimum because you wouldn't see as many auroras, you wouldn't see as many CMEs, you wouldn't see as many solar flares. Solar wind will also be weaker. Obviously, the opposite is true for solar maximum. Because solar wind is weaker during solar minimum, the heliosphere will be weaker. So, as I'll show you in a minute, when the heliosphere is weaker, it shrinks, and when the heliosphere is stronger, it expands. So over this 11-year cycle, it basically expands and shrinks, sort of like a breathing cycle. And obviously, we have reduced solar radiation and diminished auroras compared to solar maximum, where we have a lot more of that. That's why last year was our solar maximum, which is why I was able to show you those two photos of Cape Town having those auroras. So this is another visualization of what solar minimum looks like against solar maximum. So we've got all of these solar prominences, which we call magnetic field lines that you can see. you can see all these solar prominences on solar maximum because you can see the sun's magnetic field is a lot more tangled, it's a lot more active, and compared to solar minimum, where you can practically see nothing, it just looks like your regular old star. If you were to look at something, at the top and bottom of the solar minimum star, you can see a lot of straight lines projecting out. That's also the sun's magnetic field, and that is sort of us visualizing that the magnetic field does work proper. And this is actual footage, by the way. And if I was to show you the sunspot equivalence of it, solar minimum, practically no sunspots, nothing at all. Usually you'd have one or two, but in this footage we have nothing. In solar maximum, obviously you can see lots and lots of sunspots, lots and lots of magnetic field lines, crisscrossing, tangling, the like. Now, because we can see that stark difference in sunspots between solar minimum and solar maximum, that makes it easy for us to track whether we are in solar minimum and solar maximum. So, if you have very little sunspots, you are likely in solar minimum. If you have a lot of sunspots, you're likely in solar maximum. So this is just a graph from NASA of raw data. So you can see these individual points, either taken once every month since 1928. So that's about 100 years ago to 1950. And you can see they've been counting sunspots every month, and then they've been plotting it on this graph. And you can see over 11 years, it drops to a low, then it climbs back up, then it drops to a low, and climbs back up. So we've got this purple line, which is a smooth line, which we use to sort of pinpoint when solar maximum was. So in this case, you can see next to, I believe that's 1948. 1938. That would be solar maximum, and then you have another one right over here next to 48, 49. I mentioned that the heliosphere bleeds in a sense because you've got this heliosphere expanding and shrinking, and this is what that looks like. So you can see the solar system over there, and the heliosphere is much, much larger than the solar system. This crooked orbit is the orbit of Pluto, and you've got the termination shock, which is the inner boundary, and you've got the outer boundary, which is being compressed, and then it's pushing back, and it's being compressed over this 11-year cycle. All right. So why do we want to study all of this? I mean, solar events isn't the sort of thing that you will see when you look at the sun directly, which you shouldn't. Well, it's had a lot of historical impact on our planet, and in the future, if we ever want to explore other planets, explore other solar systems, it's very important that we understand the mechanisms with which our sun works, so that we work with the sun rather than against it. So, if obviously I talked about the Carrington event happening in 1859, it disrupted telegraph systems because that's what we had back in the day. And if something like that happened again today, as I mentioned, global communications, GPS, satellites, digital banking, all of that would be down. Early satellites, back in the early days of solar exploration, were also damaged by solar radiation. And back then we didn't know as much about it as we do today. So obviously future satellites can be more robust to prevent damage from solar radiation. Then another reason, which is pretty important, is that lower periods of solar activity. So if we were to say the solar maximum wasn't as intense, the peak didn't really reach that high, that's a period of low solar activity. That's been directly linked to the Earth being colder. So we've had this recorded climate cooling back in what we call the mound minimum. This is a period of low solar activity. And it affected agricultural yields that year because the environment's colder, plants don't grow as well, and that affected society. So we're very interlinked with solar weather in that sense. And obviously, how that would affect us in the future is if we were to see more periods of low solar activity, that would continue to cool the Earth, and that would combat the effects of climate change. But if we had higher periods of solar activity, so let's say the troughs weren't that low and the sun was still quite active, that would accelerate climate change because that would put more energy towards Earth, and you'd have Earth heat up even more. Obviously, there's the problem of radiation whenever we talk about solar weather, and we need to understand solar weather more so that we, as a species, can go to other planets. We can see Mars with our own eyes rather than send spacecraft to view it. And another thing is solar maximum, because if we're disrupting GPS, then obviously your good old compass won't do any good. It will also be disrupted because the compass relies on magnets, and these particles are charged and they Alright, so now that we've talked quite a bit about the sun's magnetic field and the 11-year and 22-year cycle, I wanted us to talk a bit more about the sun's life cycle, which is from the birth of the sun all the way to what happens at the end. And it's quite reminiscent of a pressure cooker. I'm not sure how many of you have used a pressure cooker, because it's practically a war between two forces within the sun throughout its whole life. Alright, so around 4.6 billion years ago, as I'm sure you're all aware, the sun was born. It had a disk of gas and dust, and it had a strong gravitational pull towards the center, and that gas eventually collapsed under its own gravity, and nuclear fusion began. And as nuclear fusion began, you had a protostar form, which is a technical lingo for a young star. So as the young star was born, it pushed a lot of solar wind outwards, and this solar wind also pushed the lighter elements to the outer edges of the solar system. It also formed the heliosphere, because now the sun starts pushing out solar wind. We've got a heliosphere forming. And an interesting thing to note is that the sun only shone at about 70% of its current brightness, which in stars is a huge difference, because that means that the sun wasn't able to provide enough energy for the Earth to keep water liquid. So we've got a few theories floating around that because the sun was young, it was more aggressive, it was more violent. You can link the sun, you can link a stellar life cycle to a human being's life cycle. The young sun was very aggressive, very vibrant, and solar weather was much more prominent. So as a result, that additional solar weather was able to provide that extra energy difference and keep water on Earth liquid. And so in a sense, if this theory is true, we have powerful solar storms to thank for us being here today. So after the sun was born, it entered its phase, its current phase, and that phase is a main sequence star. So the sun is currently a main sequence star. It's going to remain in this phase for about 10 billion years, as you can see, from 4.6 billion years ago to about 5 billion years in the future. And during this phase, it converts hydrogen to helium through nuclear fusion, and that provides a consistent energy output. So the war I was talking about between the two main forces of the sun is one of these forces is radiation pressure, and the other force is gravitational pressure. So because you've got all this gas and all this material in the outer layers of the sun that's really heavy, trillions, quadrillions of tons possibly, it's all applying an inwards force, a very strong gravitational force that's trying to crush the sun's core. But because you've got fusion and so much energy, so much light, so much heat being produced within the sun's core, that pushes everything outwards, and effectively the light output of the sun balances its own gravity, and the sun is stabilized as it is for another 5 billion years. Now, what will happen when the sun runs out of hydrogen? Because if the sun runs out of hydrogen, we can't fuse hydrogen into helium anymore, so the sun is unable to output the same amount of light and heat, and as a result, radiation pressure weakens. What that means is gravitational pressure will start taking the upper hand, and gravitational pressure will start crushing the star's core. So this will happen about 5 billion years in the future. There's nothing to worry about right now. As the sun's core starts getting crushed, it'll start to heat up, and the pressure within it builds. And obviously, because we have, at the moment, hydrogen's run out, you've got no heat being generated, no light being generated, the outer layers of the star are receiving no heat, no light, so they start to cool, and as they cool, they expand. They expand to about 260 times its current size. The sun, as massive as it already is, it will be 260 times more massive. So the outer layers are cooler, but the core keeps becoming hotter and hotter and hotter. Eventually, it's hot enough to start fusing helium. And once it starts fusing helium, like now you have a new element being fused, you have radiation pressure being output again, and then you've got that balance between radiation pressure and gravity restored. So the core will be much smaller, the sun will be much larger, and the sun will be fusing helium into carbon and oxygen. And that phase of the sun will be called a red giant. And in the red giant phase, because the sun is burning helium, the core is much hotter, it will be burning much brighter. Solar wind will become more prominent, and any of our inner planets, Mercury, Venus, and Mars, will probably stand no chance. We will be burnt away. This is a visualization of what a red giant will look like. So this is Mercury, and as the sun's outer layers are cooling and expanding, You can see Mercury just completely didn't even stand a chance. This is Venus, and the sun just swallows it. Venus didn't have a chance as well. And we predict that it might swallow Earth. Again, this is 5 billion years in the future. So we can't really make very, very accurate predictions about it. But the Earth might also be swallowed by the sun. Alright, so let's say the sun ran out of helium as well. So the sun has started fusing helium, but it's only got a finite amount of helium. It starts burning it, until eventually the sun's done burning helium. So the same process, the same war sort of resumes. You've got radiation pressure again. Your radiation pressure, gravity begins to crush the sun's core again, and the outer layers begin to cool again. And with the sun is not that big of a star. So eventually the core, gravity will crush the sun's core completely, and that will cause the sun to effectively start its final demise in a sense. What that means is you're going to have solar flares be extremely powerful, such that the sun's outer layers will rip themselves apart into space, and the sun effectively disintegrates. The outer layers of the sun effectively disintegrate, and you're going to have what we call a planetary nebula. And what's going to happen to the core is it's going to be crushed until electrons will start fighting themselves. So you're going to have the force between two electrons pushing back, and all these electrons pushing back against each other will be the only force that will fight gravity, and then this will be the final stabilization of the sun. So now you've got this tiny little white dwarf. So the sun will be a white dwarf now, and you've got this tiny little Earth-sized object that is about 60% of the original mass of the sun, but the other 40% is probably left. And as a result, because we've got the solar wind collapsing as well, the heliosphere will collapse, and because the sun has lost 40% of its mass, the planets' orbits will change. A lot of the planets might just escape the solar system. A lot of very, very interesting stuff. Now, this is just a quick diagram of what are the byproducts of what the sun is fused. The sun fused hydrogen into helium, and it's currently fusing hydrogen into helium at billions of tons a second. It will fuse helium into carbon and oxygen. So when the sun eventually dies, hydrogen plus these elements are what it disperses into space. So you've got hydrogen, helium, carbon, and oxygen. These four elements are going to be dispersed into space by the sun. But let's say we had a star more massive than the sun. What would happen is, as that star runs out of helium, its core continues to be crushed. But because it's a big star, its core is crushed enough such that it generates enough heat to fuse carbon and oxygen. So then you'll have carbon being fused into magnesium and helium. Magnesium and aluminium. And the process keeps repeating. Runs out of carbon, fuses into magnesium and aluminium. Runs out of aluminium, fuses into iron. Now, iron is the final limit. No star can fuse iron, and get a profit by doing so. So what happens is, I'm sure we've all heard of a supernova. So stars that are this massive will either explode in a supernova or they become a black hole. So this brings us to a very important quote by a very important astronomer back in the 90s. His name is Carl Sagan. If you Google him, you'll find a lot of stuff. He's done quite a lot to this field. And one very famous thing he said is that we are made in the interiors of collapsing stars. Because if I go back to my previous slide over here, you can see we breathe oxygen. Life on Earth is carbon-based. And metals like aluminium and iron is in our blood. And magnesium as well. So we've got all of this within us. So we are effectively made in the interiors of collapsing stars. We are remnants of stars. So you can think of yourself as recycled material from the star. Now that we've talked about all of this stuff, I want us to talk about a bit more about the material. Well, not materials. The spacecraft we've used to study all of this information, right? And missions that are currently still studying the sun and giving us a lot more data. So I'm going to do this in chronological order. I'm going to start off with the earliest missions all the way to now. So the earliest missions are the Pioneer missions. So these are two spacecraft. They look like this, and this is a drawing, a cartoon of sorts, because these spacecraft were launched in 1972 and 73. They didn't have computer-assisted design back in the day. So we've got another spacecraft like this in space. and their objective was to conduct flybys of Jupiter and Saturn. Once they did that, they just continued heading out of the solar system. Currently, they are outside the solar system. They provided observations on how the heliosphere interacts with cosmic rays, and they explored interstellar space, which is space between two stars, interstellar. And they also measured solar wind properties, because you started off at Earth, which is really close to the sun, and you went all the way out to the edge of the solar system. So you can just track how wind sort of depreciated as you moved on towards the edge, until you eventually reach the heliopause, which is no solar wind. Following the Pioneer missions, the more famous ones are the Voyager missions. So the Voyager missions, again, 2 spacecraft, so our total spacecraft count is now 4. These 2 spacecraft were launched in 1977, and these spacecraft were designed to explore the outer planets and cross the edge of the solar system into interstellar space. So they explored the outer heliosphere, which is the heliopause, and they also explored the termination shot. And they provided a lot of data because they were newer. They were about 5 years newer. They provided a bunch more data on the heliosphere and how it interacts with interstellar space. This is the animation behind this slide. Is the path that these 2 spacecraft took as they exited the solar system. You can see over there is the inner planet Venus. There's Earth, the blue line. This is Mars. They haven't even reached Jupiter yet. But this is what the Voyager spacecraft is. So you've got 2 of these in space. You've got 2 of the Pioneer missions out of the solar system. So you've got 4 missions out of the solar system. Now, for the 5th one out of the solar system is New Horizons. New Horizons wasn't actually built for the Sun. It was actually built for Pluto, as you can see over there. Because we hadn't ever seen Pluto up close before, and this is the only mission to have visited Pluto. So this was launched in 2006, July 14, 2006, to study Pluto and other objects in the outer solar system. We call that the Kuiper Belt. And it provided a lot of data on the heliosphere's outer reaches and how it interacts with the Kuiper Belt. The Kuiper Belt is basically a bunch of rocks and leftover material from when the solar system was made, and this is just hanging around the outer edge of the solar system. And this, again, this is New Horizons, and that's okay. So now that we've covered the 5 spacecraft that have exited the solar system, let's talk about the missions that have come close to the sun, just like the sun up close rather than from all the way over there. So we've got the Solar Dynamics Observatory, and this is a huge one because all the visualizations, all the real-time footage I showed you, most of the real-time footage I showed you in this presentation so far comes from this spacecraft. So the SDO has contributed a lot when it comes to real-time footage of what we've seen with the sun. It was launched in 2010. Its primary objective was to study the sun from the Earth and near the Earth, and it constantly monitors the photosphere, which is the area of the sun you can see. It tracks sunspots and solar flares, and it offers detailed imaging of sunspot formation, as you saw those visualizations. Again, this is the spacecraft thing. And it's also got this instrument on board, which we call the helioseismic and magnetic imager, which maps the sun's magnetic field. So again, the visualization of the green and purple poles, the spacecraft thing. Finally, we come, second last spacecraft. This is the Parker Solar Probe. So the Parker Solar Probe, I hope you've heard of it, because it's made headlines last year by being the spacecraft that holds the record for coming the closest to the sun's surface, the sun's gaseous body. So it's got a surface, and it came 6.1 million kilometers from the sun's surface. And it is the only spacecraft to date to have entered the sun, because it entered the sun's outer atmosphere, which we call the corona, and it's currently there. So this is the only spacecraft that we have that has entered the sun and is still operational. And again, if we think regarding solar weather, if the sun's emitting so much radiation, so much solar wind, CME, solar flares, for a spacecraft to get that close and for it to not melt from all this radiation, it's a pretty huge achievement on behalf of engineers and scientists that made this. And it also goes to show how much we wanted to understand the sun, so that we were ready to build something of this magnitude. It also discovered this fancy thing we call magnetic switchbacks, which is basically how solar wind starts off from 0 and accelerates as it moves up to the towards the rest of the solar system. Finally, the most latest spacecraft is the Solar Orbiter. This is a collaboration between NASA and the European Space Agency, and this was launched during COVID years. And its primary objective is to study the sun's polar regions, its heliosphere, and its magnetic field. So it also captures high-resolution images of the solar corona. I didn't manage to include any in this presentation. It also studies the connection between the sun's surface and the corona, which is to say it studies those layers in the photosphere and the chromosphere. And it also provided the first close-up views of the sun's polar regions, so we were able to understand the sun's magnetic field a bit more. So we've got all these spacecraft working really hard to improve our understanding of the star that's closest to us. Okay, so now that we've talked all this about the sun, I just wanted to talk a bit more about how we can observe the sun if we wanted to, because I've talked quite a bit about how scientists have done it, but if you wanted to look at sunspots for yourself, this is how you're going to do it. First off, never look at the sun directly, not through a telescope, not through binoculars. You will instantly burn your eyes. The sun is very, very bright. It's got a lot of harmful UV and IR rays, ultraviolet and infrared rays, that are too strong for our eyes. If you look at the sun for long enough, you will probably lose your sight. If you look through binoculars, you will focus all of that sun's light onto your eye, so that will be even worse. Unless obviously you have telescopes that have solar filters on, which scientists do. So if you wanted to observe the sun on your own, you can use one of these. These they're solar glasses. They're useful for watching eclipses because these you cannot see through them right now. That's how dark they are. The tint on them is really, really dark, and what that does is it reduces the brightness of the sun to something we can observe. If I go back to the section, this is what the sun looks like through one of these. You can see this is during an eclipse, so you can see sort of a crescent sun, and around it you can see how bright the sun is. You can see the sky completely blue. So one of these will help you look at the sun directly. Obviously, you've got to take your precautions. Before you look at the sun, you've got to just make sure the tint is fine. You've got to make sure that it's not damaged or scratched in any way, because you cannot risk your sight. You only get one set of eyes, so you've got to make sure these work. Now, people might try to give you fake solar glasses. The easiest way to check is there's a certification, international certification. It's ISO 12312-2. On these solar glasses, it's written right over here. So those of you that get yourself a pair, you can just make sure that they're valid and not cheating you out. Okay, we're done with the presentation. It is now time for a quiz. Before we start the quiz, I just wanted to point out this image is really interesting. This image is called the smiling sun because we've got 3 sunspots, 1, 2, 3, and 4 times 1. Okay, time for the quiz. So this is how the quiz is going to work. I have about 10 questions. 10 questions, yeah. And if you, all of you can try your shot at a question. But if you get one question right, you get one of those. I'll give it to you immediately. And if you get one of those, you won't be allowed to answer any other questions, because we want to give everyone a chance to get themselves a pair of these. So if you answer a question correctly, that's it for you. You can obviously discuss with your friends. You can leave answers to them. You're welcome to do that. Okay. Question 1. Start off pretty easy. What is the sun's current stage in its life cycle? Okay, it's not for you. Main sequence. Any other answers? Nobody? Nothing? Okay, that is because yes, the sun is the main sequence star. So you will stop on this. So if you look back at the slide, when I talk about radiation gravitational pressure, we can see that from 4.6 billion years ago to 5 billion years in the future, the sun is a main sequence star. Okay, moving on. What is the approximate speed of solar wind traveling through space? I will start with you. Okay, do you have any other answers? No? That's correct. So, if we look back at the slide, solar wind travels at roughly 400 kilometers a second. You've got yourself another pair of solar glasses. Alright, moving to question 3. What is the hottest layer of the sun? Is it the photosphere, which is the layer we can see? Is it the core, which is the center? Is it the solar corona? Or is it the convective zone? Fun fact, the corona is actually hotter than the photosphere. The corona burns at about 1,000,000 degrees and the photosphere is about 5,000. Yes? The core, right? There you go, it is the core. It looks really pixelated here, but the core burns at about 15 million degrees Kelvin, which is similar to Celsius. It scales in a similar way. And you've got, it's decreasing all the way till the photosphere, and then you've got the corona at about 1,000,000 degrees Kelvin. So you also do this up. Alright, moving on to the next question. I'll try to keep it as easy as I can. What is the duration of time needed for a solar magnetic field to be? I think that made it too easy. Yes. 11 years. Do we have any other answers? Everyone thinks it's 11 years. Alright. It is 11 years. So we've got 5.5 years is the time it takes to go from the trough to the peak, which is solar minimum to solar maximum. 22 years of the Hale cycle, where it completely returns to its original state. And 44 years is just a random time frame. Alright, next question. What is the primary cause of solar flares? Is it magnetic field reconnection? Is it the collision of solar winds? Is it nuclear explosion on the surface? Or is it gravitational clouds? Magnetic field reconnection, any other answers? Yes? Nuclear explosions, any other answers? No? Okay, so it is magnetic field reconnection. So you can see we've got huge magnetic field here. It snaps over here, it snaps over here. This end reconnects to this end, and this end reconnects to that end, and this whole piece goes towards the planets. We've got another, okay, so it answers you. Alright, next question. Where on the sun's surface is rotation the fastest? You'll remember I showed you that fancy visualization where you had purple and red, and we've got 4 areas. We've got the chromosphere, the corona, the equator, and the poles. Yes. The equator. Any other answers? Yes. The poles. Any other answer? Okay. The sun's rotation is fastest at the equator. It takes about 25 days to rotate once. At the equator, it takes 34 days to rotate once at the poles. You get yourself there, so Alright, next question. This is a simple one. How many spacecraft exit the solar system? Yes. 5? 5? 4? Anyone else? Okay. Yeah. Yes? 4? Yes? Answer? Okay. It is 5. Now, firstly, that's a correct answer, but before I elaborate, bonus question, whoever can name all 5 of them, get another answer. Wait, did you already answer? Yes?
5 year, 10 and 11.
Yes.
Voyager 1 and 2.
Yes.
And the new 5 years.
Yes. So that's all 5 of them. Alright. Next question. How many types of solar flares are there? Do we have just one type of solar flare, magnetic reconnection, and we're done with it? Do we have 5 types of solar flares, 7 or 3? Yes. 3. Okay. Anyone else with a different answer? No? Cool. It is 3. You've got, if you recall this slide where we had a fancy solar flare popping out of here, you've got X-class solar flares, M-class solar flares, and C-class solar flares. So that is correct. Here we go. Alright. How close did the Parker solar probe, launched in 2018, get to the sun's surface? Was it, because remember, it was launched by NASA, that's just a little clue there. Was it 6 million kilometers, 3 million kilometers, 150 million kilometers, or 6 million miles? Yes. Any other answers? Yes? No? Yes? 3 million kilometers? Yes? 6 million miles? Okay, so despite American units existing, in space we use kilometers. So the answer is 6 million kilometers. It's actually 6.1, but we can obviously round up and say 6 million. 150 million kilometers is the distance between the Earth and the Sun. That's the final fact. Okay, so who was the first who said 6 million? Yes. There you go. Alright. So what will happen at the end of the sun's life? Will it become a white dwarf? Will it become a supernova, spreading all of those elements throughout the solar system? Will it become a hypernova, which is a massive, massive star supernova? Or will it become a black hole? Who has an answer? Yes. Pardon? White dwarf? Black hole? White dwarf. Okay. The answer is it becomes a white dwarf. If we look back at this animation, you can see the sun in its fragile phase, extreme solar flares absolutely ripping the sun's outer layers apart, and you'll see gravity crushing the center of the sun down all the way till it's about an Earth-sized white dwarf that holds only 60% of the sun's mass. So we've got ourselves another answer. Yeah, there we go. All right. Bonus question, how many times larger is this red giant than the sun? Yes. 260, there we go. Right, I think we're almost out of questions. What is the outer boundary of the heliosphere called? I think this is the last question. Okay. I'll go, yeah, anyone else? I'm willing to give away 2 solar classes for this one, since this is the last question. So if you have an answer, you can raise your hand, choose an answer. If you're right, you'll get a solar class. Yes? Heliopause. So we have 2 heliopauses. Any other? No? Yeah. Okay. So it is the heliopause. So we've got 2 pairs of solar classes right here. There we go. So a few important terms here are that obviously the heliopause is the outer boundary of the heliosphere, but you've also got the termination shock, which is the inner boundary of the heliosphere, if you remember this animation. And then we have this really interesting thing called the Oort cloud. The Oort cloud it's a bunch of just comets and very far objects from the sun that orbit the sun, that we think orbit the sun, and they lie much, much further than the heliosphere does. It's a really interesting thing. It's like a complete sphere of just comets and stuff like that. Obviously, I talked about the Kuiper belt being comets beyond the orbit of Neptune, close to the heliospheric boundary. Yeah, I think that is it. Yes. Thank you very much. This is not what I'm here. I want to ask any questions.
Once again, thank you everyone for coming, taking part in the quiz and taking part in the presentation. I definitely really enjoyed it, and I want to say that that's the same for a lot of us here. Thank you so much. And yes, we're looking forward for hopefully more presentations to come. And please, whoever can, wherever you can, please be involved with the Astronomical Society of Botswana and wherever you are. It's interesting stuff, so if you do have interest, continue to learn about these things. So yeah, thank you.
Do you have any questions? Yes, what is your question?
Don't be shy. You can just ask.
By the sun. Okay, so it's a bit out of the scope of this presentation, but the keyword, I guess, in this sense is magnetic switchback. So the Papa Solar Probe studied magnetic switchbacks, which is the phenomena through which particles, as they're released from the sun, are energized and then thrown into space. And what one is not.
Outstanding presentation. How do we know that the Carrington event occurred?
That's a good question. I'll be honest, I'm not too sure. I'm not too sure how we know how the Carrington event occurred. I'm assuming I'm assuming historically they did keep track of the telegraph system going down, and then scientists in the modern day tried to backdate that and then figured out that something of the scale of the Carrington event actually did take place back then, and that's the probable cause for planet-wide telegraph disruption. I'm assuming it's an explanation for that. Yes?
Since the hot cloud is not the sun, you assume. Does the planets in the not just about the solar radiation?
No. So the solar radiation doesn't necessarily melt anything, but solar radiation is just charged particles. When I said spacecraft like the Parker Solar Probe would be melted, A is because of the sun's heat, and B is because it's electronic. So because it's electronic, you have charged particles messing with it. That's what I meant by melted in that sense. This temperature of the vacuum of space is minus 270 degrees Celsius. So those things will stay well frozen, rock solid, and because they're so far from the sun and from any other star, they will not be heated to melt. Yeah. So yeah, question, yes. No, so it actually goes on for quite a bit after. So we have a lot of other objects in the Kuiper belt that orbit the sun, and the heliosphere encompasses all of that. If I were to say in light terms, I think it takes about 30-ish hours for light from the Earth to reach the edge of the solar system. So where the heliosphere is, it takes about 30 hours. Because when Voyager was there, whenever we used to communicate with that spacecraft, it would take 30 hours, it would send a message, it would take 30 hours for it to deliver, then Voyager would see it, and then it would reply, take another 30 hours to get back, and then we'll get a response in 60 hours. So that's how we do it. Yes, yes.
I'm just curious about the spacecraft that are going into space. Like, what happens to them once they're done doing the job? Because I know there's no article about space race and how much they're thinking space.
Yes, so a lot of that happens. So we've got a lot of space waste floating around in space. Obviously, you've got the actual spacecraft itself. If we were to look at something like Voyager, there's no plans to bring Voyager back to Earth. It's gone. So it's just going to be floating around there. It's going to be pushing onwards of the solar system. And other spacecraft within the solar system as well. They're just orbiting there. They're going to probably, if they collide with something, they collide with something. But not only do we have that spacecraft just hanging around in space, but also the rocket that was used to launch it. Because once the rocket launches it, the spacecraft detaches from it. But both the rocket and the spacecraft are now out of the Earth's sphere of influence, out of Earth's gravitational field. So now you just have both of them just there. So that's why we have companies, private space companies like SpaceX, developing reusable spacecraft, because it's expensive to create a rocket for it to be only one time, use one time. So you have things like Starship, where you have this huge rocket goes into space and then it comes back as well. Yeah.
So you're talking about spacecraft that are closest to the sun.
Yes.
So I wanted to ask, what was how do I say it? What made it? What is the how was the spacecraft built such that it might just melt as close as the sun?
Okay, so I know there's this material, sort of a gold-looking material that sort of blankets the thing, sort of like you would wrap a gift. It wraps the entire spacecraft, and then obviously in front of the Parker Solar Probe, we've got a huge shield. So both of those in conjunction work together and prevent the spacecraft from overheating, as well as melting from radiation. The exact specifics of how that material does it, I wouldn't know. I believe that's classified information. Yes. Yes, so 2024 was our solar maximum for this sort of decade, and I'm sure you heard on the news in May 2024 there was a geomagnetic storm, G4 solar storm, we called it. That's its category, and we also saw auroras. So we are now exiting that period of solar maximum. So there will still be quite a bunch of CMEs and solar flares that we will continue to see, but by the time 2035 rolls around, we will be in complete solar eclipse. So yes, we will see quite a bunch of solar eclipses. Yes.
Still about the spacecraft that touched the sun, right? It was communicating back,
Yes.
right? Did the radiation not disrupt that? Like, how is it still able to communicate?
Okay. Okay, so yes. So we've got the sun over here, and we've got, let's say, Mercury, Venus, Earth, and so on and so forth. So what the Parker Solar Probe did, and this is just me talking about concept, this isn't how exactly it was, but Parker Solar Probe orbit was something like this, right? So it's elliptical in the sense that there's a time where it's very far from the sun, but there's a time where it's very close to the sun. Because if it was close the whole time, it wouldn't stand a chance. So when it's close to the sun, let's say from here it enters the sun's atmosphere and here it leaves the sun's atmosphere. For this entire period, it's just recording. It's observing, recording, making measurements, using its cameras to look at stuff. And then once it exits the sun's atmosphere, once the radiation levels drop enough for it to be safe, then it starts communicating to Earth, transferring all of that data to us. And obviously, there's the obvious thing of if the Earth was on this side of the sun and the spacecraft is on this side, we don't have a line of sight with the spacecraft, so you can't talk to it, you can't see it. Any other questions? Yes.
About the spaceship that got the closest to the sun.
Yes.
Isn't it the sun has its own gravitational force, right? And so do the three planets closest to the sun.
Yes.
So how do the engineers that made that ship ensure that the gravitational distance of all the other three planets doesn't affect how it moves the ship?
So, the three planets, Mercury, Venus, and Earth, their gravity wasn't actually the villain in the story, it was the hero, because getting to the sun is difficult. So getting to this point is really difficult. It's the equivalent of me driving a car at 300 kilometers an hour and using the engine to stop the car, because the Earth is orbiting at really high speed. So what we did is we used Earth's gravity, Venus' gravity, and Mercury's gravity to help slow us down. The process is called a gravitational assist. So you could Google a gravitational assist and you'll learn a lot more about it. But the general idea is that it used their gravity instead of being used by its gravity. Yeah. Any other questions? Yes. Well, it depends. As far as I'm aware, we don't understand enough about the sun to predict solar flares so far in advance that we could do meaningful stuff to prevent it. So what we do, it's hard to predict, but considering that in 2024 we didn't have a blackout and that was our absolute maximum, we shouldn't have any for the next 22 years, or 11 years. Yes,
Very fine presentation, Acharya. The next closest star to us being 4.2 light years away, Centauri. Would the dynamics, or do we know of the dynamics of Centauri as much as we do know of the Sun? And are the dynamics similar to the Sun as you explained?
I believe the dynamics would be similar in a sense. It is possible that the solar cycle period might vary, simply because, as far as I'm aware, Centauri is also a dwarf star, a dwarf, like the Sun is. But the problem with Centauri is its magnitude is 11 point something. So it's really difficult for us to observe with the naked eye. Obviously, telescopes could observe it. So I'm fairly confident we wouldn't know as much about the solar cycles of that star as much as we would about us. For that, if any one of you wondering, solar magnitude, apparent magnitude is just how we measure the brightness of something. So the lower the number is, the more visible it is. So 11.6 is not visible at all. Something that's visible is usually lower than 0. So you have something like -1, -2. That's just an explanation. Do you have any other questions? Yes.
Wonderful job. Very nice.
called Julian saying that you still
Oh, it's solar prominence.
so what?
It's solar prominence.
So what?
Solar prominence. The one, so solar prominence is basically when solar material is being held in an arc-like shape from one sunspot to another, and that eventually can go into a sun.
Oh, yes, because I think you said that you still
Oh no, so that usually is where magnetic field lines do cross, but that isn't magnetic field lines.
yes. That was psychology.
Any other questions? Alright, thank you so much for attending.